Hello, everybody. Thank you for coming. My name is Miloš Manić. I'm a professor of computer science at VCU. I'm director of VCU Cybersecurity Center and also director of Commonwealth Center for Advanced Computing, known as CCAC. Today, I have a great pleasure to present three speakers from IBM. You can see them here, Anna, Benjamin, and Marilyn. I will let them introduce themselves. They have a very impressive positions, expertise, and story to share with us. The story is tied to centerpiece of Commonwealth Center for Advanced Computing, IBM Z16 machine that we refer to as simply as supercomputer. The CCAC started a number of years ago. In 2022, state approved nearly $7 million to support advanced computing across the Virginia. As part of this initiative, we have acquired this machine, which soon will be available for first prototype users, if you will. I'd like to thank everybody for coming. I'd like to thank our speakers. We have a number of people from Northern Virginia and Fairfax and Mason, from IBM in the Fairfax region. I'd like to thank Len for connecting and making this happen. And without further ado, I really want to give time to our speakers. Anna, you will go first. Thank you very much.
Thank you. I'm going to try to share. So as Miloš said, he asked us to collaborate and present to you today, sharing our joy of what's next, but everything is about computing. My name is Anna Topo. I'm a Chief Technology Officer and a Distinguished Engineer at IBM. And it is truly my joy to talk about those next evolutionary steps that we are all taking, especially since you're gonna see, I originally come from semiconductor area. I have my PhD in physics, but I've been doing a lot of work in all those other areas that we're gonna talk about. And so hopefully that would come through. I cannot just jump in. I really want to give a credit to the people who are really working on the topics we're going to be discussing, and those are people from our IBM research labs. We have really amazing group of folks who are scientists, engineers, designers. By the way, they're all from all different fields. I just wanted to say we have people who have backgrounds in medical, user experience, social, and so forth. So that really allows us the diversity of thought that is so needed in the future, and especially now. As you can see, we're really focused on semiconductor, artificial intelligence, quantum computing, and Marilyn will talk about this, and cloud as an underlying layer. But we also cannot forget about security. And we also think about accelerated discovery, which is projects that connect all those capabilities together. So I manage Think Labs, which are what I call places where our partners come to meet with the researchers. These are the various labs that we have across the world. And again, what I'm going to talk about touches on the work from all those labs. So I just really wanted to give the credit to them. So why we do what we do in IBM research? Clearly, we're an IBM sub-organization. So clearly we are there as an organic growth engine for the IBM corporation. But I think the one thing that really joins the motivation for all of us who are in the lab is this ability to create what's next in computing. That is really our passion. And so if I was to describe what really motivates us is that we continue to develop the classical computing, so the world of the bits. That you will see, and you will have a presentation from Benjamin, strongly continues on. In meantime, of course, we are now in the world of AI, So we really have to address all the needs from the AI world, which we called the neurals world. And of course, we cannot forget that we have this paradigm of additional computing engine that is the quantum computing. And that is very important to us because at the end, in the future, we hope to have the reality when all of us as users come with the applications, come with the problems, and it's an integrated part of the hybrid cloud automation and work distribution that really allows us to engage with any of those computing capabilities. So let me quickly start with the semiconductors. Please ask questions. Milos gave me only 20 minutes, so I'm not sure how we're gonna do all of this, but please finish. Okay. So again, starting with semiconductors, I have to say this. In 1971, when we started with the transistors, not many people think about this. The transistors were in micrometer size. Now we have transistors that are nanometer size, 1,000 times smaller. It doesn't seem that huge, but if you really think what it took us to get to this, it's amazing. And that's why we carry devices everywhere, right? That scaling really led us through this innovation. The innovation now is not just scaling down in the nanometer technology, but creating completely new structures and architectures. The vertical transistors, the nanosheet transistors, and of course, future analog will be coming to us as well. Benjamin will talk about our systems. I really wanted to comment as this is what drives us in research to focus on the devices because we have our own products, right? This is our capabilities. And I cannot be more happy that the fact that you have it as well. I think from the future of the education we have to give to our students now, they have to understand various types of computing system, how they're gonna be integrated in the future and be very adaptive to the changes, right? And understand that the DevOps of the future will be really communicating between all those systems. I'll give Benjamin the opportunity to talk about all of those things, but no, I don't have to say it. Just imagine those systems run 375 billion transactions per day. I just, again, from the point of view of the scientist who lives through various development of where we got, it's absolutely incredible, right? I just want to remind everybody. All right, why we are passionate about semiconductors? If you are a person who's just running applications, you may say, oh, it's the backend, right? That yes, interesting, but maybe not as much. I will tell you that in the world of AI, truly driving the compute capacities, this is the AI age, we have to really think of what's next. How are we gonna support those capabilities? The AI, and I will show in a second, is extremely compute hungry, and that requires very different look of how to invest in those new technologies. And that's why you see here many of the countries really investing in the semiconductor technology. Just last week, we had announcements from Vermont, where the government of Canada and Quebec state specifically, we're talking about really new investment in packaging, because it's the chips, is the packaging themselves as well. None of the companies can do it on their own. This is, the race to keep up with the technology is so huge. We have an experience over the last 20 years. We always partner with others. We have strong collaboration. And if you ever have a chance, and please let me know if you wanted to come visit our site in Albany to really see the collaboration in action and really seeing this facility, research and development facility, please let me know. All right, what does that mean? That means that we are driving expectations from the classical computers. And what you see right here is that new development on our own Z system, which is in this case, the Telum processors. You see here a capability of doing the standard, doing 8 processor cores, adding the standard what we need, which is the memory. But in addition, we already know that that's not enough. We are adding the actual AI core. So what you see here on the very, very edge, because we know we're gonna be doing more. We're going to be doing inferencing. In the future, of course, we're gonna have to address the training as well. And so this is really huge. And again, Benjamin will, I'm sure, touch on this. That is important because those models are compute hungry. We are throwing at them a lot of GPUs. That's, CPUs and GPUs. That's what we do right now, but we're gonna need to do more. And so example of this particular AI unit, of this AI core, was that it actually lowers the latency of the inference activity of the AI model specifically. And you can see it almost 20 times because you're giving it a very specific action to do it at the core, right? So your latency of coming out of the chip is much slower. But this is the graph that really drives us all. Over the many years, we had the traditional expectations, which was that compute will double every 20 months. That was our expectations, and we were all set to meet those demands. That changed with the advance of AI, and that expectation now is compute doubling every 6 months. That is huge change in the traditional roadmaps and architectures. And so what that means for us, we are really thinking, what are those new accelerators that we're gonna have to create? One of them, for example, is taking that AI core that I just talked about from our own Z processor and putting it as a chip on as a package on a chip, right? SoC, putting it in the actual nodes, building actual servers out of this, and using it very effectively for the inference capabilities. This is the actual unit that is built and is in our Yorktown Heights laboratory. Again, if you're interested, I'm sure Marilyn is going to invite you there to see our quantum system. But if you want to see those new advances in AI, please come join us as well. And finally, this is where I'm going to state the AI is driving the new infrastructure. The AI is driving development of new models. The AI is driving our ability to really think what we do with data. A lot of thinking of this whole supporting management of what we do. Most of the people think still that AI use will be, I will either buy a product, right? So I will buy AI infused product, or I will do an API call to some type of solution, or I will play with a vendor who has a platform for me. And so in our case, we really took a strong look of what we need to develop for ourselves. And the story that I'm going to tell you is really what we did for ourselves so that you can more project it on what does that mean to you and other organizations. And the story was very simple. Like, we all in the research develop our models, and everybody does. I'm sure in this audience, you all been participating in the last 16 months and for a few years now in developing their models. That process of finding the right data, training those models, and most importantly, developing the validation for each of the models was done separately. The large language models came, taking the bulk of the work to create one language model. So the training, let's say the model development, and then now we have opportunity to just reuse and reuse and reuse this one model. Before we couldn't reuse, we have to every single time create a new model. Now we can reuse those models just simply by tuning them. For us in IBM, that was huge because we know we have data and capability in specific areas. And so we really thought, what does that mean to us? So we created a model called the Granite model. So you can see right there, 20 parameters. We trained them on 1.6 trillion tokens. And that model was then trained and trained and trained to do specific things, understand and write code. So translate the language and then write the code. For us, I think this is huge because in the future, I don't think we even understand how much more DevOps and AI programming will come to all future generations. This allows us, and I will give you here just an example. I'm asking the system to write a program in Python in this particular case to return all pair of numbers which have a difference that is less than a given threshold. Anyway, the system just understands the language and gives me a Python number. Then I actually ask the system to now translated from Python to Java. And the system does the translation. Now, I may not trust the system, so of course I'm going to ask about documentation. The system does the documentation for me. I'm going to ask the system to really give me code explanation, and the system does it. For me, that is huge, because that really leads us to next ability that is so important to us in IBM. We have many systems that operate on COBOL. We want to train as many students as possible in COBOL, but everybody has their favorite coding program. Now we have opportunity to simply, as you can see right here, transfer COBOL knowledge into Java. That is much more mainstream for many of our students and many of our new developers that will be working with us, right? That really changes the landscape of AI for the future, because it evens up opportunity for many of the developers before, and evens up almost a ground between data scientists and developers who can more evenly participate in our ability to create something new. Now, I did wanted to state that that is huge, but it points out to something that those large language models still need to be truly trained. So if you took just ChatGPT and try to ask the model to create a Python code, then ask ChatGPT with additional pairs of actually showing them the Java pairs of understanding of what we want, versus this particular program, this particular model that was really, really trained to do this job, you will see the difference. But the comment is they all came from the large language model. It all came from the one core of the language of the model that was trained to do a more general job, right? And proving again that those large language models will make a difference to us. And so I just wanna truly take a moment to go over this slide. I know Miloš said 20 minutes, I'll cut slides on there. Quantum computing, because Marilyn is here. But for me, this next slide is where truly we all need to look for, especially as we are educating the next generation of our students in AI. First one, the data importance. I just wanted to comment on this. We know we need a lot of good data. A lot of data, yes, volume is important, but we just showed how quality of the data. By the way, when we trained our model on doing the Python to Java translations, we did it once, and then we actually had to remove some of the pairs that we created that we didn't think were good enough. And when you train the model, removing the codes that were not as effective, you actually get the model working much better, right? And so the quality of the data is incredibly important, but the volume of the data is still there. This is quite amazing, but if you look at the Gartner reports, the Gartner is saying that within next 5 years or so, 99%, I think it's 98.5% of the internet will be loaded with AI data. I couldn't believe it, because I thought, we've been loading internet with so much of our own data that there's enough for us to last for a very long time. That's not what Gartner says. Gartner says that we already are loading, everyone tried ChatGPT. If everyone is loading thing on internet that is now AI embedded or has some type of generated AI content in it, right? And so it's in a very short time, it will be hard for us to really identify the original data versus the AI data. And so the value of the clean data is incredible. Looking at time. All right, second one is the model alignment and tuning. Every single organization that is using AI, it doesn't matter if it's in a healthcare, it really doesn't matter which applications we are using, is going to see that we will have a teacher model, and then we will have a student model, and then we'll have a critic models. We will have this ability to enhance our ability to do faster AI workloads and faster AI application, and by the more accurate and so forth, because we are in a way using AI as this creator of this training data. So AI will create a lot of synthetic data. that will allow us then to create a better data for the models, tune those models, and we will have a critic data that will be validating those models. That sounds incredible, but it's already happening. If you look at the world of AI, all you hear is the self-X, I call it, self-alignment, self-correction, self-evolution. We call it the self-play. AI is really enabled. And I think that is huge. But that puts on all of us, the educators and the people who are responsible for those technologies, responsibility on trustworthy AI, ethical AI. If those systems are doing all those things, then it's all on us who are building those systems to really think about this. Number 3 is architectures. We have, of course, all the discussions about you train the model a lot and then the model is hallucinating. But I will tell you, we already have methods that you can train a huge language model on a lot of data, and then you add just external memory with a very specific data. So think about a corporate policy. So if a normal model will give you a specific answer that is very loosey-goosey, you can do this or you can do this. That embedded memory allows you to compare your answer, the original model answer, to what's embedded in a policy, and then the model will only choose the answer that is correct based on a policy. That is huge for many enterprises, because now you limit the hallucinations based on your specific views of the world, your specific policies that you want to infuse into the model without actually giving the huge boost of data. Before, I had to bring a lot of data. Now we proved that you can do it with 200 lines of code. It's a small chunk compared to the tokens, multi-billion tokens that we are using before to train the models originally. So that is huge. And then the second one is, as I said, the multi-model models will be even more important. We know that large language models are not good at math. You give them a mathematical problem to solve, the language they will describe the problem will be great, good English and all of those, by the way, Polish and all the other languages too. But if you actually look at the math itself, it's often not correct. And so now we're getting to this architectures are changing, because models will be calling other models. Models will be calling what we call accelerators. So model will know that if I'm asking for some mathematical calculation, I will, at this point in my answer, go out and actually use a calculator. I will call an API. I will call a different model. And before my answer comes, it will then be coordinated together, right? And the answer will come. This is what we call this multi-model. And more importantly, this is what we called the compression need for those models. Because just imagine models calling models, models being very large. How can a developer, a person who actually wants to work on models, do all of this when a model on its own needs huge amount of GPUs? And I think this is the biggest difference between now the world of the DevOps, where if you think of DevOps, I can call API, I can have version controls, many people can work on one software at the same time. If you think of a world of AI, when you think of, it's a very, very simple one, Llama. We all heard model Llama. It's not that I can create a Llama model and somebody else comes and updates that Llama model. It's more like a tree. We had the Llama model, I create my Llama model, you create your, it's a forks. So we are not collaborating on them, not creating together versions, we're forking in AI world, right? That has to change. And the only way this can change is that we have to allow each of us to actually have access to this model. And the only way to do this is to quantize the models. You have to create, and this is the work that is very important, right? You have to create software developer kits that allows you to quantize the models so that you spread the joy of updating them, right? And joy of really creating a better skills and capabilities for those models. All right, so this was the really enjoyment of doing this. Again, the same as in semiconductor, one company cannot do this, right? I just wanted to say This is huge. There's a lot of responsibility on all of this, right? So it takes all different organizations to really think about this. So I really hope that you all look into the AI Alliance, see which one of your partners who you already partner are in AI Alliance, because there are some very important topics we have to address. And I'm just listing them right there, right? From regulatory policies, of course, to abilities to advance testing and validations, the ability to really create an open source access to the models and so forth. All right, and the final is the quantum. Since I have a benefit of Marilyn going after me, I can skip a few slides now. So all I just want to tell you is that I am a physics major, but I will not spend the rest of the 3 minutes on telling you what the quantum computing is. But because what I want to show you is that it really doesn't matter what your background is. The quantum computing, so the back end is already here. All of us as a users just simply have to now realize that I can connect to it, and you can through the cloud. We are still at the early stages of the quantum computer, that you still need some skills, developer skills, to really get into cascades and the software programming of those systems. But you can see it right here. The quantum systems we are building, right? This is a quantum system 2 that is in our laboratory. And this system is modular. It doesn't just has one quantum computer chip. It has multiple computer chips that are being enabled. We're gonna have to, in the future, really understand, if I come with the workload, what workload will be run on a quantum computer? What workload will be run on a classical computer? And maybe there is a specific application that has to be split. Parts of the workload goes to the quantum computer, parts not. And we have a very good understanding what are the appropriate workloads for quantum computers, which are not. And we have a lot of experience, as you can see on the left side, with the very specific topics that are appropriate for quantum computers. And with that, I just wanted to say we also have proofs over the last specific proofs this year that we hit capabilities of the quantum computer that in the past, we often had classical computer to simulate what quantum computer will do. That's what we always did. We always use the simulators. For the first time, the quantum computer with only 127 qubits is more effective of doing that simulation than the classical computer, right? So we hit the utility era, and with our ability to continuously work on the error correction for quantum computers, this is the one that I just talked about, this multi-qubit system that was able to do this, prove the utility of those quantum computers. We truly now have capabilities that your students could be accessing. Marilyn will tell you how. I just wanted to state, right, there's a process for it. But we are at that junction where you have classical computers, when you have AI systems, when you have quantum computers, and the next generation of students should know that's what they're gonna be using. And yes, they cannot use it yet on a phone, almost, but you could connect to the cascade through your phone, right? You can probably not run yet your simulation, but many companies already do. Many companies are really utilized in all different industries, are really talking about combining various workloads and specifically thinking what the workloads are for the quantum computer. And again, Marilyn will talk about this. So this is my final 2 slides. I am, as you can see, very excited about the fact that we are in this new world. We are not there yet. To really connect to all those systems, we have to be better at applications, the APIs, the infrastructure, the users, because right now we have almost those things separately. We're optimizing each one of them separately. So you have the AI, the classical computers, the quantum computers. I told you, we're all having roadmaps how to make them better. But the future is really in the interoperability. The future is really in the integration and interconnectivity of those things. And that is, for me, the most exciting part for the next 5 to 10 years. We are already showing how much AI helps us here, because it's all about automation. It's all about having one call and not 10,000 calls, API calls to everything you want to do. And I think this is really the future where you can do your work much more effectively. And with Miloš right here, having your System Z and power systems, he didn't say power system, but I said he has power systems too. Access to AI units, we have now ability to benefit from those other systems. I just wanted to say, the future is here for what we call this multi-cloud computer for AI. And here, this is what I'm going to end, because I think this is the most exciting part. We can absolutely prove already that we can do amazing AI work. So this is the work we did with NASA, where we developed the geospatial model in IBM on IBM infrastructure. That model was then fine-tuned in NASA at their own environment. That model came back to us for inference, but it was all heterogeneous and was all done right. And you can see amazing results of creating such models. So I will finish right here. I will let the other speakers talk. And I just wanted to say this was the first presentation, and Miloš knows that if additional deep dive presentations are needed, we volunteer to bring additional speakers. Thank you.
Thank you very much. We're racing against time. I would ask you to try and ask a question in real time while Ben is getting ready. Ben,
Thank you. Anna, you have done sure.
he can take over. And while Ben is getting ready, I want to ask Reza, who I talked to yesterday, to briefly, just in a couple of sentences, reference the advantage of IBM system when it comes to GPT type of applications, real time.
Yes, sir. One of the technologies that we have in IBM Power is called the MMA engines, which we have plugged into the processor itself. So it's not it's very, very low overhead in the system. And what it does basically, it allows the architecture within the power system to allow your data, where you get and clean your data in Anna's picture there, to do inferencing right there. And by doing that, you are going to make available lots of different solutions, lots of different with that architecture capabilities, where you can in real time tune your model and inferencing. Right? So let's say there are lots of data out there, 95% of them getting obsolete within 5 minutes. You need that data to be tuned quickly, and you can use that information immediately. That architecture allows you, and that's not something we have, for example, in ChatGPT. If you ask a question, what is the latest code on something, it's going to tell, well, as of 2024, January 15, I have this information for you. And that's because models are developed here and they are inferenced someplace else. This is not the case. This architecture that we have enables us with this type of functionalities.
Thank you very much, Reza. So in interest of time, Ben, go ahead. The floor is all yours.
All right, thank you. Hello, everyone. I'm Ben Siegel. I'm sorry I couldn't attend in person today as I'm recovering from, excuse me, ankle surgery due to an unfortunate skiing accident. But I am on the up and up, and otherwise I would have loved to have be there in person. I'm a senior technical lead in IBM Z research. I'm focused on AI, security, and regulatory compliance initiatives, and I work closely with several business units across IBM to ensure that our research agenda aligns with the business needs. I actually spent half my career starting in IBM Z product development, architecture, and design before taking on a position with the Watson Jeopardy research team just after the Jeopardy system handily defeated Brad Rutter and Ken Jennings in the Jeopardy Human vs. Machine challenge back in 2011. And just after that time, I led multiple teams to productize and adapt the Watson research technology to the healthcare domain to improve patient care and reduce physician burnout by integrating AI technology into EMR systems. But over the last few years, I've come full circle now back in Z, bringing what I've learned from the Watson space and over into my current Z research role. All right, now I know Anna spent a moment on the pervasiveness of Z, and if I were able to see the audience and if I were there, I'd probably ask for a show of hands. How many of you have withdrawn cash from an ATM, or how many have checked your banking account balances in an app, or if you've purchased anything at a retail store? I got to imagine everyone by now, right? All their hands would be up. And congratulations, you've touched a Z system somewhere, probably even used one today. And I have to admit, when I graduated from college some years ago, I wasn't aware of Z at that time. It was System 390 at the time, so I guess I'm dating myself somewhat. But when I found out that anytime I attempted to buy something, anything, make some form of business or banking transaction, most likely a Z system was involved. And so that was an eye-opener for me, knowing that one line of code could touch billions of users at once. So today, IBM Z kind of goes without saying, it powers the world's economy. It's probably no surprise that banks are the top adopters with their highly regulated environment, their need for scale, compliance, security, and performance. So we have IBM Z represented across at least 28 industries and 73 countries. And although relied upon by businesses across multiple segments and markets, Z is particularly important for highly regulated industries, as the platform enables businesses to stay up and running with like 8 nines of availability now, growing IT capacity on demand, ensuring data is protected, and helping remain compliant with regulations. So Z really does build reliability, availability, and serviceability from the ground up, from the hardware all the way through the software stack. But of course, I wanted to spend a few moments on the AI stack in particular. So I'll move from left to right, and we'll focus on some of the AI innovations we've made from the hardware throughout the software ecosystem. And we look across the 3 dimensions: AI at scale, AI ecosystem, and AI agility. From the AI at scale, we built an on-chip AI inference accelerator as part of the Z16 Telum chip. It natively supports the AI operations required to accelerate deep learning models like LSTMs, RNNs, CNNs. And we've shown that the credit card fraud detection models that we built could handle 300 billion, with a B, billion requests per day, with each request served within a 1 millisecond response time, which is just frankly amazing to wrap your head around that. This is especially important for what we call transactional workloads, like credit card purchases, where detection of fraudulent purchases can be detected in near real time. AI is embedded within the business critical workloads, and we ensure that the transaction completes within the appropriate amount of time, also having understanding that there could be more than 60,000 transactions happening a second, and each one of them had to be served within a few milliseconds of response time. The second part is the AI ecosystem. So we've embraced and contribute to open source AI technologies and have brought many of the popular AI frameworks and tooling to IBM Z, whether it's TensorFlow, PyTorch, XGBoost, SnapML. Many of them are supported directly on the platform. So not only do we have the open AI system ecosystem to Z, but we've also built in optimizations to ensure that it's performing well and that you can transparently and seamlessly benefit from the optimizations and the acceleration. We've also integrated the open source technologies in our product offerings, which I'll talk to in a moment, and also intend to deliver it as part of our WatsonX.ai tools for IBM Z. The third part is AI agility or frictionless AI. So that means that the training, if you so desire, could happen in other environments, whether it is a different on-prem infrastructure or whether it's a cloud-based infrastructure. But the model that is built, it can be deployed back on Z16 to exploit the new AI accelerator chip. So build, train anywhere, and deploy on Z16. So next, I wanted to spend a few moments on the chip itself. So the maximum Z16 configuration, it has 32 water-cooled chips serving out up to 40 terabytes of memory. Each chip has 8 cores that Anna was showing before, with one built-in AI accelerator. So this equates to 200 usable cores for all the other demanding workloads that could be running on Z, and 32 on-chip AI accelerators. There's a highly efficient hardware caching protocol in place that allows direct memory access to the AI accelerator from the cores on the chip. There's centralized on-chip accelerator it's shared by all cores. It's very low and there's low cost and consistent inference latency, even if all of a sudden there is a spike of tens of thousands of transactions happening at that same moment. The compute capacity and the bandwidth is optimized for scale, and all of the typical memory virtualization that you get that runs on the typical cores also is also supported within the AI accelerator as well. So there's an optimized data transport to the chip, and then there's a set of unique neural network instructions that can offload the instructions and operations for deep learning directly onto the accelerator. And then it has its own transformations built within the instruction set as well. So it's very quick and direct to get the data from the inference, from the payload, and then provide the score out back to the asking application. There's no data duplication or copying in the sequence, and it gives over 200 teraflops of compute power on a 32 chip system, enabled for security and AI accelerator that works with the standard Z core processor. Now, before I go on, are there any questions so far? Okay.
Ben, I have one suggestion.
Sure.
The stats, the numbers you're showing might be going a little bit way over the head for some of us. Can you put in simple terms, how does this IBM technology relate to what we have at traditional GPU, high performance computing centers, traditional
Right, yeah.
stuff?
Sure. So the net of it is that with about half the compute power, it can serve out, say, 3 times as many requests. And I have some examples that I'll go through in the credit card fraud space that talks specifically on some of those numbers. But the big value add here is that we can significantly do more with a lot less in terms of minimizing the power requirements necessary, and able to still provide just as much inferencing capability at a much lower response time. So let me talk a little bit. Actually, let me just skip ahead here because I want to make sure that Marilyn also has a chance to go. So I mentioned this before. There's also capability where we in the infrastructure take advantage of that AI compute power. So we built out something called DB2 SQL Data Insights. So in addition to exposing the AI accelerator to an end user application, we also exploit the AI accelerator transparently in our flagship relational database, DB2, and we call it the DB2 SQL Data Insights. It's a technology that is built into DB2 that enables different views of DB2 business data without the need for data science skills. So what we've done with DB2 is embed a neural network model within the DB2 system itself. It trains on DB2 data. It analyzes relationships and patterns within the data across all of the records and columns. Then, using simple queries, you can explore and analyze relationships in the data that aren't seen with traditional SQL queries. And actually, an example of that was partially what Anna was showing before in one of the dashboards. We use SQL Data Insights to detect insurance claim fraud by analyzing claims made based on where weather disasters and geographies are happening, and then determining if the claims requested are in line with other claims made in that area. So they're much easier, they have a much easier time of filtering out what are anomalies based on insurance claims coming in relative to weather patterns in the area, and much easier to see with the additional deep learning analysis that's performed within DB2 itself. So the key there is that there's no data science skills that are actually necessary, and you get out of the box capability within DB2 itself. Okay, so we know that AI on Z, it's delivering value in a lot of different industries. I just wanted to give you an appreciation for the breadth of AI that we see here, impacting many industries, and here's just a sampling. While the majority listed here are in finance, we also see medical image recognition, data redaction and data de-identification, climate change impact, cybersecurity, and geospatial analysis, to name a few others. But on the fraud detection side of things, and thinking about AI at scale, and getting back to your point, we worked with a large bank to ensure that the bank could score 100% of all their transactions. They couldn't before because they were offloading to an x86 GPU server farm, which introduced a lot of latency. So only about 10% of their transactions were scored in inference in near real time. But with the Z16, they had the scoring engine that was now moved on platform, on the chip, and they're able to scale without any additional penalty. And so now they have 100% real-time scoring. So that's one, certainly a value add here. But the other one, if I had to showcase one other example here, would be in the medical space. We worked with a large medical group, an IBM partnership with the Z16, where working with the medical group, we built an image classification model to adequately identify different stages of prostate cancer in biopsy images. And so they built models for detecting and classifying the severity of the prostate cancer based on images of the samples. And from the move to the Z16, they were able to see that the inference time of running against the images was 75% faster compared to the GPU server, and that their AI inference workload saved about 41%, or 41 times, I should say, energy consumption. So it was a big energy consumption saving, along with being 75% faster compared to the GPU server. Okay, so I did want to hit a little bit on the landscape, with the main point of emphasis being that, and as Anna already mentioned, the impact of AI is enormous. The economic impact is measured in the trillions. And when we look at the compounded annual growth rate of AI, we see significant expansion in both the financial and the cybersecurity domains. So many job opportunities are going to follow, and we need to build these skill sets now, as well as being responsible stewards of the technology. So what we're seeing now in the AI landscape, there's a new paradigm, and Anna was touching on this too. We see a Venn diagram merging between traditional AI and foundation models. With the foundation models, they're built using a specific kind of neural network architecture called the transformer. Now, the transformer helps the foundation model understand unlabeled data and turn an input into an output using the self-supervised learning. The ensemble AI is a concept where we're trying to actually use and unite traditional machine learning with foundation models. So one example that we're exploring is using a foundation model like BERT as a secondary model in fraud detection scenarios. So the first model could be more of a traditional machine learning model that's used to screen transactions. And then for a subset of transactions that fail with the initial screening, they go to a much, I'll call it heavier weight foundation model. And then we run through the secondary foundation model to leverage additional data that we're then capable of performing additional analysis. And so there's this general move in the business world as well, over to the foundation models, which then gets us to some of the questions that Anna was talking about before. So I won't spend too much time on this, but I will say that if we have to look at how it was trained, garbage in and garbage out, as was mentioned before. We have to make sure that what is going in to the model is carefully understood and governed appropriately. And we have to detect and minimize if bias and hallucinations are happening. So this elicits several areas of active research, identifying bias, hallucinations, explainability, and all these are going to be cornerstones to moving towards trustworthy AI and enabling that across all of our platforms. So here is where I wanted to give an example of some of the research work that's going on in terms of AI alignment. And this is where you can define like a contract of what the AI needs to provide back to the end user. In this case, it should be honest and accurate and engaging, provide diverse perspectives, be ethical, do no harm. And what we see here is that sometimes the principles might not be fully fleshed out. And so in the prompt here, we see the question of, well, there is a man and a woman. Who is a nurse? And the response, let's say, comes back with, the man is a doctor, the woman is a nurse. Well, that's certainly discriminatory and sexist. And if we go and look and we say, well, if we can define a principle that the AI should produce respectful content that is free from offensive, discriminatory, or harmful material, it should not participate in endorse risky activities. So if we then add this as a guiding principle and ask the question again, who is a nurse? Well, now we get, I don't know who is a nurse. So that's better than before. And let's see, I just wanted to look at my time quickly. Let me pause again, see if there's any feedback.
Thank you, Benno. We do need to wrap up, but thank you. Any questions for me?
We have a large health system here, and I'm curious, you showed one image of pathology. How widespread is the usage in the health science, healthcare sector?
There is a pretty large representation, not necessarily imaging, but over on the electronic medical record side. So for imaging at this point, probably a bit less, but we do have some engagements that are active, and yeah, be willing to explore more with you. Are there things that you have in mind in terms of like other aspects of medical imaging?
I think we can talk both about EMR and imaging. Both are important areas for us. Sorry, you had your hand up. So both would be potential areas that we could talk about.
Okay. Yeah, and I know I didn't have a lot of time to go into security. I'm happy to do a follow on with that, where we can go through some of the aspects of security that we've built into the platform as well, and specifically how it can relate to healthcare.
But just a quick one, for infrastructure like this, when you talk about deploying in a data center environment, I was recently at the NVIDIA GTC conference in San Jose and subsequently at Intel AI Vision in Phoenix. There's obviously a lot of talk about the new GPU-based infrastructure taking somewhere around 120 to 150 kW per rack when it comes to a 42U rack, just standard across the data center industry. Can you give a bit of perspective of how this infrastructure compares to a GPU-based fully stacked rack?
So when you look at what a fully stacked rack, and a lot of their NVIDIA cards are fairly power hungry and probably in the potentially up to 300 watt range. Everything that we're developed here is much less than that, such that, I mean, we're orders of magnitude different. But having said that, and then thinking about what Anna was mentioning too, the card form factor that we're looking at, trying to if we're going to compare the GPU servers to Z, a little more of an apples to apples comparison would be to have these potential cards that Anna was mentioning plugged in as well. And in that case, in terms of how we're sizing it, we're making sure that the wattage is very minimal, nowhere near, certainly nowhere near 300 and under the 75 watt mark as well. And so we are looking at making sure that we optimize the power footprint for the compute.
Yeah, I think if you go to GPU farms, any of you who've ever been hot and loud, I think that's all you can think of, right?
Yeah,
If you
right.
go to our
Exactly.
AIU unit, I mean, you just simply open the door and you can continue talking, right?
Right.
It's the AIU units, use literally 45% of the power that you need for it.
Yeah.
So that's huge, but I'm going to say, we all gonna need GPUs, right? Because there's training, there's an inference. And so I think the future is really of creating, and I'm calling it rocks, but creating your infrastructure that benefits from the fact that you have those other accelerators. So for inferencing, you don't dump everything on GPUs, and you don't dump, you really do much better integration of the semi-homogeneous infrastructure that you can run.
Yeah.
And by the way, lack of in the US, I don't think we really appreciate, we have more access to GPUs. It's not the same worldwide, right? And so,
Oh, absolutely, it's not the same. In fact, I was working with one of my clients in India.
Yeah.
They got the first deployment of 16,000 GPUs, and they stood up the first, it's called the Shakti Cloud, a public cloud architecture, which is purely built on GPUs, which is phenomenal. Onto your point, right, just, so what that's driving even the GPU-based architecture is paradigm shift when it comes to the power design, let alone cooling is another,
exactly.
Ballgame altogether, the different types of cooling technologies. But even when it comes to designing, architectures to support that kind of workloads, I mean, I think the entire industry is trying to come to terms with what that really means and to what extent they have to go back to the drawing board and be able to support these equipment.
Excellent question. We have been working on this, and
So
we
let's
are
make it
now
up and make sure that we give time to Madeline, but go ahead.
That's one reason we went with 7 nano technology.
That's
Nano. So for the new processors we have, he's rushing me, so I am stuttering. But that's why we want those processors, like in MMA that I mentioned that are in GPUs, be where they are. So there is no waste of energy going someplace else, getting it, bringing it back.
Yeah.
So I can tell you the power server we have right now, Power 10, we call it, is using 50% less per core, even though it is a lot more powerful than the previous version. So sustainability is one of the key design points and being green in these solutions.
But I think in the meantime, I'm just thinking really heterogeneous, some GPUs, some CPUs.
Of course, I mean, the
some
heterogeneous
AIs.
environment, that's a given for, absolutely, that's a given, yeah.
And your
Alright.
CCAC
And
environment,
quantum computers, let's and Mary, with
and
quantum.
and your CCAC environment here has Z and power.
We have 3 power plants, but Maryland.
Okay, hello, everyone. I'm Marilyn Wagner, and I run quantum computing from a business development perspective for IBM in the academia and for the US government sectors. And I want to give a big thank you to Milos, who helped organize this along with Anna, as well as some others that I'm going to mention. Now, I am from Manhattan, so things run in a New York minute for me. And I realize that we are woefully over time. So it's 11:39. How much time do I have, Milos?
20-ish.
Okay, so the only thing preventing you from eating lunch is me, and I get that. So just raise your hand if you have a question or, someone on the line here, but I'm going to go through this pretty quickly. Oftentimes it's the better part of a day that universities come and talk to us at Yorktown. So I'm aware of that. Alrighty, so in reflecting on what would be important if I was sitting in your shoes, I thought I would go over the IBM quantum ecosystem, as well as what's IBM's differentiator. And it really comes down to our technology and the error correction around that. And how it specifically relates to you is we desperately need to build the quantum workforce. Okay. Now, as a show of hands for those in the room, do you consider yourself you're very knowledgeable on quantum? Okay, there's just a couple of hands in the room. Okay. Alrighty. So IBM Quantum's mission is to bring useful quantum computing to the world and to make the world quantum safe. We're going to focus on the useful quantum computing because we have a whole nother business unit that talks about the quantum safe. So we're really with quantum. We started back in 2016 to really bring this mission because of our heritage. And as you've heard from my colleagues here, we started, that is our heritage. So we're building upon that. And we very much have a philosophy that, a lot of universities have supplanted in them, the Z computer or whatever classical computer. So it's a matter of building on top of that. So what you heard from my colleagues, this is a let's work together environment. Quantum utility is upon us. We're going to go into that and what that really means. But I really want you to leave this, our time together, knowing that from an IBM quantum perspective, it's about our technology and about how we're going to be able to solve the world's most complex problems through error correction. Because right now it's about qubits and it's about gates. And IBM is arguably the leader. I mean, check it out on your own, in terms of being able to get to the most complex problems of the world. I mean, wouldn't you want to work on something where, you're solving, a specific disease, like cancer or climate change or, fraud and what happens in fraud. So, and you do that through the algorithms that, quite frankly, people in this room would be working. Now, there's 3 different areas within quantum, and it's superposition, entanglement, and interference. Think of superposition. I like to use the example of if you have a penny and you flip it, it's heads or tails. That's classical computing. Now, if you take that same penny and you spin that penny, think about every other iteration on that penny. I mean, it's massive. So working with a classical system to do the sort of heavy lifting, but then the quantum computing from the algorithm perspective, that's what's really game changing here. And then entanglement to share the information, and interference is the noise part I was talking about. So classical computers are suited for a lot of really good problems, and we are at the beginning of the journey on quantum computing. So we're going to be able to really unlock those problems that classical computers historically cannot. So there's problems that we can't address adequately today, ones we can, and then ones that we eventually will. So when you think about quantum computing, think about hardware, software, and then the resources that are like yourselves in the room are using to develop on top of the quantum computing. Okay. We have, the hardware we have, like I said, it's been out since 2016, and we are very focused on the innovations that are going to take us to that error correction standpoint. Then we also have a layer where we are basically the de facto standard with our Qiskit. I don't know, has anyone ever heard of Qiskit? Okay, great. So it's the software that you use on top of the hardware. And someone that is very conversant in Python, it would be an easy upskilling for them. And then in terms of learning, actually I have a couple of slides on that. I'll wait on that. Yep. Okay, so we have a very large ecosystem, and I hope that you all consider joining the ecosystem on some level, because we offer free training for those of you that are interested. We have the largest base, and what's really important is that when people use our quantum systems, they write papers on them. Like they're working collaboratively in their own universities and whatnot, and they're writing like really important, what they were able to do on a quantum computer that they perhaps couldn't classically, and they're writing papers on it. And we have the largest fleet of quantum computers out there. So in terms of accessing a quantum computer, we do that through our QICs, or quite frankly, anyone can log on to like IBM Quantum. You get 10 free minutes a month. It used to be a lot more, but because we have the 100 qubit and above computing available only, that's why we changed that. But anyhow, it'll, you can do a simulation classically and then move it over to the quantum computer. But we're global. We have 39 quantum innovation centers, along with 8 dedicated systems. And 8 dedicated systems are those that have come to IBM and said, hey, we literally want a box either on site or it'll be at your site, and then we can have it just for our own use. So what is a quantum innovation center in a nutshell? There's 4 pillars to it. It's research and development. It's using quantum as a tool in the workforce enablement, as well as the ecosystem development, because we realize we can't do this alone. Now, this is an example of those that are on the quantum innovation network. And, it's really industry leaders like, company names you may have heard of. I realize you can't read this. As well as research institutions. We work very collaboratively with a lot of universities, and then startups. We're starting to do a lot more in states where we collaborate with state governments. Tends to be companies, or I'm sorry, universities that are heavy into the research component, and then they sort of have this incubation arm. So it seems to work out quite well. So let's talk about the learning platform. I encourage everyone to go on the learning platform. And the reason for that is because there's different pathways on the platform, whether you're a senior level person that you don't need to be developing algorithms, but you want to understand quantum. So we have a pathway for that. But if you are that physicist or the person that knows Python that wants to know more and how to develop algorithms, there's different pathways for that. Free of charge, because we really want to build the quantum ecosystem. And, we have over 8 million learners globally, over 4,000 courses. And because of the way Zoom is set up, I can't see the last one. Oh, okay. We have over 1,000 active users. Now, you're probably wondering, okay, well, what do you do with all this hardware and software? And we break it down into these 3 different working groups. But let's drill into healthcare and life sciences for a moment. We have literally 11 different groups working on these problems right now within our healthcare and life sciences vertical, and these are the papers that they're writing. I'd be remiss if I didn't mention our roadmap. Basically, IBM set out this path, and we said this is how we see the vision of quantum computing from a, if you look here, it's the hardware, then we have the middleware, and then the applications in the code assist on top of that. And I think Anna mentioned that we have gone through a single sort of processor to, we believe that we are going to solve the world's most complex problems through a modular approach. So we announced it last year, and we're pivoting to this modular approach. We have this quantum system 2 in Yorktown, and that's going to help us get us there, because the key really is in 2033. You know, we put a stake in the ground saying that we are going to be error correction by 2033, actually technically 2029, and then error mitigation to then. And we have many papers that are moving that along the axis that proves we're going to be able to do that. And you say, well, really, you might not do that. Well, that's true, except that if you see those little green check marks, we've achieved every milestone that we've set. I can skip over this one. And Anna mentioned this, but one thing I'd like to say is that the 2 things that you look at with quantum computing are the cost and then the circuit complexity. So if you continue along that axis, it's going to be pretty darn expensive to do what you need to do to solve these complex problems with a classical method. So today we're here, okay? And we believe that we're going to get to this quantum error mitigation and then quantum error correction, and it's going to be a lot less expensive than what you could do classically. We've published a couple of papers that prove our theory on this. This was the first one that was published last year. And after that paper was published, you know, there were arguably some skeptics that went out and tried what we set out, what our thesis was, and they support our theory here. So in terms of the capabilities, you know, here's some statistics on sort of the tools for the computational scientists. But the thing I want to draw your attention to is that we are by and large the de facto standard with our Qiskit software, and it's supported. It's not just proprietary to IBM. There's over 8 hardware manufacturers that also use our Qiskit software. Okay, so in this chart, I wanted to get here because what this does is basically shows you where here you are as the user, then we go to the serverless part, right? And then you can either do single or multi-node, and this is really what's going to get us to that error correction. We published a second paper last month about this error correction that I'm mentioning. And it's been an order of magnitude improvement on what we were doing previously. So we're well on our way here. Now, I've sat and put myself in your position in terms of from a university perspective. Here's what's really interesting. There are gaps to prevent us to get to a desired future work state. So how can you prepare these university students? Well, there's a big gap in terms of funding. You're all on your own there. In terms of the assets, quantum awareness, expanding the workforce. These are some common themes that we're seeing. And if you have a curriculum that attracts these students, you're going to really help them in terms of workforce development for quantum. Because there's need out there. There's an immediate need for quantum. And yes, in a few years. So it's a matter of sort of developing that curriculum to attract those students. Now, the most promising areas that you can imagine are algorithm development, right? You know, because we're still working on these really complex problems. Then we go to the error correction, and the application development is really around that use case area. We're working in a few areas. but we really need to solve even more complex problems. Now, this is a chart that shows sort of those in the degrees needed for different jobs within the quantum industry. And as you can see here, it's not as though everyone has to be a PhD in physics, because there is that upskilling that's being done. And we're working with a couple of states right now on how to do it. Let's get into use cases. Here's primarily what we're working on and where we've seen success in these three areas: simulating nature, mathematics, and processing data with complex structure, and search and optimization. And you see it runs across industry. Now, I wanted to take this particular example because with university students that I've mentored, I like to get them from thinking about, this is a really interesting problem, to what is the financial impact to society? And I can't think of a better one than in the financial services industry. So what's the near-term improvement worth in terms of financial fraud? Now, if you're looking at like money laundering every year, that's up to $2 trillion a year. Imagine if you were one of the people working on a use case to try to solve that with quantum. That'd be pretty incredible. Identity scams. I mean, I get them weekly. I don't know about you guys. Identity theft, credit card fraud, and fines levied by regulators. And with that, I think I did that in about, 15 minutes? So if anyone has any questions, I'd be glad to answer them after this. So thank you so much, Miles.
Thank you very much. Really exciting presentation, and I don't think any of us are surprised to be surprised. So thank you again. Question, comments? I do have one, but I'm gonna let
So I have some questions both about this and in general. So I heard the presentation on quantization and its importance. A lot of early IBM work came out of there. You also did a lot of the work on actually doing the quantization on hardware devices like memristors. So where is the future there? And the question to you is, we see in the academic community now, as people move away from one-dimensional computing, there is the question that quantum is compared against the one-dimensional. But if you build an ASIC which can do a specific task like optimization, then it is still up whether quantum is more superior or you can scale up this. So again, what is IBM's view in the future?
Yeah, for me, it's very simple. She showed the various applications. Classical computing will continue to be better and better and better. We'll go to analog, we'll go to next. So in some cases like optimization, quantum computer is giving only linear benefit. In other areas, quantum computer is getting exponential benefits in it. So it's really what type of problem you have. In some of them, classical computer could for a while catch us longer. In some of them, you will hit it much faster. That slide she showed is semi an average of where we are with that particular utility paper that was very specific to quantum focused applications. But you're correct, right? For some of those specific problems, it may be a little different, right, in time. But on the memory, on the AI quantization of hardware, I will come back to you. I think we just have to set up the time with the team. But you have the.
Okay, so what is your or IBM's view on quantum machine learning? And then also on your hybrid discussion, where do you foresee the Z16 connecting to the quantum work in the future?
I'm so glad you're asking this. I'm really, really serious. We are spending humongous number of hours and resources on quantum specific machine learning models. I just wanted, we have full groups that completely are addressing those problems, because I think it's the same way as you have security. You have AI for security and security for AI. And the same thing in quantum, you will have AI for quantum and quantum for AI. There will be a lot of capabilities that we're gonna have to. So we have to have new quantum models. We're gonna have to have AI that's gonna be enabling some of the workload separation to get us to this. We have AI models that help us with error correction already. We have AI models that help us with mitigation. So we have full teams devoted just to that. And the biggest goal we have is when you come to Yorktown right now, with the lab where I am, you have behind me, if you enter on the front of me, you have huge quantum computer, the system 2. On the right side, you have, as I told you, the AI units, which came from the system Z, right? This is our Telum processor. And the biggest goal of that lab is to really prove to you in the future that those computers can very effectively really split the workloads and decide which one is going where. I'm saying already, we're not there yet, but that's truly the goal of that lab, is to prove as soon as possible. We already running workloads on Z, we're already running works with AI, we're already running works on quantum. That efficient operation integration of those things is the most important part for us for our future. But we need a lot of, I just wanted to say, we're gonna need a lot of AI models to decide what goes where, a lot of integration without the units, because we still cannot lose on latencies for all those calculations, right? So it's really where the goal of our work is for next year.
Yes, I'm sorry. You mentioned the workforce obviously is huge in quantum, just like data science before that, and even we're still looking for programmers, right? I think from all these years back.
Yeah.
So what is IBM doing? Because if you don't have the people out there that can do this, then you can't scale it effectively. So what is IBM? I know you said you had the online learning platform, but outside of that, what kind of proactive activities are you doing to help build out that workforce? Because that's usually companies of your size are doing that kind of stuff to make it available.
Yeah, so we do a lot of university outreach, and I didn't put it in here, but in terms of, we do hackathons with universities. We help them develop a way to educate and really expand it throughout the community. We have mentorship programs. We have, and I think it's full right now, but we basically bring, I think it's 400 students in, and we train them on quantum over the summer. That's our summer school. So we do a lot in terms of education, both hands-on or, virtual. It would just depend on like what the university needs, quite frankly. And curriculum is really key here. Like, are you sort of educating someone on the basics? Or, what level are they, and, how do we move this?
Are y'all sharing your curriculum with the universities as well?
Oh, yeah.
Okay.
Yeah, we, quite frankly, we help them build the right curriculum for what they have, whether it's, and what I mean by that is this undergrad, is this graduate level courses, is this like skill transference? So yes, we help develop that.
And I said that the hunger for this is huge. I just wanted to say that she mentioned the quantum summer camp.
Right.
I don't know how many of you ever tried to submit a paper for NeurIPS. Like, when the tickets for NeurIPS are released, you can go to the conference within first 4 minutes. There's no more ability to register for that conference.
Right.
For quantum, we last time beat it. We couldn't even count the first minute. When we looked around, there was no seats, period. Because it's so, it's really recognized as the best way to get to it. But as you said, right, in addition to this, we have hubs. So the universities who support training of other universities as well. So they develop the curriculum and they share it with other universities.
And just to add what you asked about quantum and AI, it's one of the things that I fear the most. But for the same reason, we are working on quantum safe computing environment as well, that he was going to mention, but we ran out of time. In both platforms, we are developing our systems in a way and protect the systems against future threats when they become available.
And thank you for adding it, because that is very important.
So speaking of universities and curriculums, so I'm involved with BCU from the perspective of, we formed a Internet Ecosystem Innovation Committee, where I work with Vince Cerf, who's Google's chief internet evangelist, and diversifying the internet, creating more hubs around the world. And also I'm involved with SMU in Dallas, Texas, where we've put together a master's program in data center engineering. So it's a full-fledged master's program. So programs like that, and there's a third initiative I'm involved in at the state level with Virginia, where multiple universities are together, and we're working on kind of the implications of digital infrastructure across the board. So just curious, if there is an opportunity, as an example, in a master's program for IBM to plug in with the quantum compute, what's the best way to go about it?
Yeah, we'd have to have a conversation about that. Yep, I'd be happy to go with that.
It's easier with the general AI skills because we have something that is called the skills build, and Miloš is really interested to bring this capabilities. So that's free classes. So my free education that it relates to general AI knowledge. For quantum computing, we have specific programs, so you will have to directly
Yeah.
work with Marilyn.
I'd be happy.
Thank you.
But you had a question, sorry, we
Yes,
skipped you and I lost.
yeah, so I'm curious to know about the temperature of operation of your quantum computer. What is it now? How warm can you go? And I'm always worried about the cost of cooling, energy cost of cooling. And
Okay.
is it sustainable or not?
So I mean, we always commented 50 millikelvin is the operational temperature, and that's because we are cooling down. We have stages. You go, you use different gases to do it, and you have helium that separates and so forth, right? So there's the chemistry and physics. But the question is, how many of institutes will actually be worrying about this? How many organizations will actually be buying quantum computers versus how many organizations will be simply connecting to the quantum computers, right? So yes, right now, there's only few, and Marilyn, you showed, right? There are 8 centers that many of them are related either to big corporations that have money to invest in building their own, supporting their own quantum systems. There's only 8 so far. There will be more. There's no doubt there will be more organizations who will buy their own quantum computers, but for majority, that's why it is original goal for this was to be served through cloud. And we're really focused.
But besides quantum, the Z machines and Power 10 machines, can you reflect on energy savings, both in energy consuming and energy savings coming from AC costs, which maybe not everybody knows is really the cost of running a center.
But I just wanted to add, remember the benefit, and I'm going to be proud on this one, because the benefit we have as a company that builds the quantum computers is that we build our own Z servers. I mean, the problem of building something that is energy efficient, we've done this for so many years. So yes, we have a challenge that we don't build our own refrigeration systems. Of course, we work with vendors. So the refrigeration units, the cooling unit, the chandelier that is inside is embedded in the cooling unit. That we have to work with the vendors. I mean, we have to really continuously specify of what do we want from efficiency of those systems. But everything else, the connections to the compute that is the classical computers, we own this, right? We can design this. We had worked with many computer companies, with many vendor companies, because microwave cables that need to go in, we don't build them, the companies have to build them, right? And so it's really collaboration with a lot of vendors to get those quantum computers to the most efficient state over the time as we build them.
I have a question that I believe most of the Virginia partners would be interested in understanding path forward. And I will just put some numbers. We, through CCAC, have 3 Power 10s. That translates to 120 GPUs. Virginia Tech has 2 Power 8s, that's 2 generations behind. Translates to 96 GPUs. Nationwide, University of Illinois has 16 Power 9s. Translates to about 1,500 GPUs. UT Austin, about 96 Power 9s, translates to over 9,000 GPUs. Oak Ridge, Power 9s, they have almost 28,000 GPUs. MIT, about 2,500 Power 9s GPUs. So all of that may or may not mean much to even some of us, but we have individual HPCs serving individual universities' purposes. Industry has some other sorts of HPCs. CCAC is meant to serve the whole Commonwealth of Virginia. Can you briefly address the value of Z and power tense in terms of being unifier for existing resources across Virginia, because we are statewide initiative. So we are really all interested. We had my old good friend Alberto Cano, who is director of VCU HBC, but he unfortunately had to leave. But I promised I will ask this question and pass the response to him.
Yeah. I'm gonna first reply for for Virginia itself, but Benjamin, you know, a comment in general about the Z systems and power, because I think there's a question about what is enough for the new models. It's just a general question. What is a typical cluster or typical infrastructure that is good enough to run big models or large language models versus what specifically we could do for Virginia? But Benjamin, you want to comment on that?
Right. So the thinking could be that on the power side, you could build your models there and then run further tests on the inferencing side over in Z. And for that kind of capability, for model size of in the millions of parameters, it would scale very well. If we're talking about larger model size, like in the billions of parameters, in the next generation machine, that's where we're looking at ensuring that we'll have the compute power necessary. But a follow-up to that would be in terms of the application of this. What is your thinking on the use case here? Because that would change the demands of the amount of hardware necessary. So like a transactional nature is very different from, say, a research work that's more AI and analysis based. Right?
Yeah.
So
And by the way, I was going to say for smaller models, you can just do what you said before. You can do inferencing and training on power too, right? And so it's just depending how big the models are. But now to answer for the Virginia one, I give you an example of the models we developed for NASA, where we truly, in a hybrid mode, took environments from various organizations. So we use the IBM for doing actually creating the model. Then we use AWS, a completely separate location in a way, that environment to actually train the model. And then we did again the final inference on IBM. And so I think for me, for the Virginia, is you have to really think of this hybrid enablement and really think of applications, what should be run where, and really get to the point where you can really move models, share models, right? And I think this is the biggest part, and this is where your center can play such a big role from semi coordination of the various capabilities and how this should be done. I think for me, that's where we all want to go, into this true hybrid mode of sharing resources across locations, not on just one spot.
So you're saying the different HPCs can truly integrate and interconnect?
That would be the goal for a truly, supporting education infrastructure for your projects, for students, and for everybody.
So would that fall on us, or is there a way you can help facilitate?
That's why I think that collaboration is so important, right? We can see what the organization here, you as an organization, can do versus where the help is needed, right? I think that's exactly where we need to go.
We have Dan Han, who is CISO for VCU, and we were just talking the other day. There's something called Shibboleth single sign-on for not only Virginia, but pretty much the whole world. So in an ideal world, the user would connect with their own organization and have all these resources available transparently, not even worrying about assigning this or anything like that. So maybe then you have a question relative to that, or maybe you have an answer how that we would go about that.
And by the way, we have research projects currently that all relate to the future of hybrid cloud interconnectivity and interoperability. Because right now, we are all bounded by license. I have a license to this, or I pay for API to this. or I have a SDK kit for this, right? We're all bound by little licenses, so it's really hard to imagine how in the future it will be boundless, right? How do I really interoperate through this? And so we have a lot of projects. Our, of course, open source collaboration is through Red Hat, through OpenShift. But we collaborate with everybody else, and this would be the thing that needs to be solved, within the thing we have to all solve very, very shortly, because it impacts all of us in our ability to really deploy AI and work on AI.
But through CCAC, we currently, and maybe Len can very briefly address this, we have something called AI Ops, we have something called IBM Watson, we have something called IBM
What's on
Quantum,
orchestrated?
and so on. So this is what with single sign-on would be available to rest
The local.
our Virginia partners and possibly outside. Maybe then you can address how SSO works within BC or between universities and how you would perceive this ideally working at the
Yeah, I
level
mean,
of Virginia.
I think maybe just in the simplistic terms, really, we kind of have to figure out, okay, what are the services that we want to expose?
Yeah.
To all the numbers, right? And so, and ideally, what I'm seeing is, hey, here's a web portal, right? And then Shibboleth is a federated SAML authentication provider. So ideally, we would take in all of these identity providers from the various universities around Virginia, and possibly we can extend it out to other institutions outside of Virginia as well. Again, with this federated identity model, right? And whatever the C platform can provide is pretty much the service. So, this may not be the best platform to have this conversation, and you're gonna probably need to talk a little bit more about this, but in terms of getting all this stuff built out, and we have to know, okay, what are some of the use cases? So one of the example use cases I have, and I am a practitioner, I'm not necessarily a researcher, right? But with generative AI, for instance, right now there are a lot of folks who cannot necessarily use a lot of the public models that are out there for system data, right? Because the fact of the matter is, okay, retrieval algorithm generation, great. But the fact of the matter is, you are still sending data to these public models. So in that sense, what about harnessing the power of generative AI with some of the more sensitive data that we may have? I mean, do we have some type of private isolated environment that we can use? And I think that in itself can be a use case, and that would help me because
So I think it's both. You have to think of the isolated environments where the researchers are able within Virginia geographically and so forth share the data and inference and do all the training models. And the best thing to do it is on one common application. So your comment about imaging, like if there were a few professors, right, that really wanted to learn from each other and do this together, right, then you create, I call it, the common data lake, right, that is secured and governed by the organization. But that's one versus the semi-broader interconnectivity between various locations within the Virginia educational system.
And we can talk about it later, but we have a confidential computing architecture that can be used. So nobody can look at whatever everybody else has if needed. And then also the AI platform that we have has a module that helps with making sure all the ethic rules between different categories, and we can share that with you for the different time.
But for the software development, which even before the AI, we talked about federated learnings. Like we have a good concept developed before for software DevOps. Now we have to really create the same environment for AI models.
Now, Len, maybe you can briefly address what capabilities
sure.
We had through IBM partnership right now, starting with their ops and so on?
Sure. CCAC is, again, based on the Z system as the Power 10 systems with associated disk and so on and so forth. And what is being implemented on them, so it's universally available across the whole state, and even above with your single sign-on capability, is something called IBM Cloud Infrastructure Center, which is based on OpenStack and Red Hat's OpenShift container platform. Then on the power systems, it has something called Power Virtualization VC. Stands for
That's right, virtual.
Virtual service.
No,
Or the
VC,
many-
Power VC, Power VC.
Yeah, virtual service.
This is one of my power guys. And the Power VC does what ICIC does on the Z, on the power machines. And that, on top of that, will be an umbrella called IBM AI Ops Operations. And that will be the interface out to the world. So this looks like a single hybrid cloud based on all that architecture, accessible. It will know how to deploy dynamically where the workload works best, whether it's on Z, Power, or a combination thereof, and maybe even how to connect into maybe something like Google Cloud or AWS or something like that. You might want an IBM with a cloud too, where you work with that. So it's just about done with being installed, and we hope to have it working here very shortly. I would say within the next couple of weeks.
What kind of services are you gonna be providing with that platform? I mean,
When you say, what can you define what you mean to me by
like,
services?
so you're saying there's a, public cloud presentation, so what? Again, just in layman terms, as an end user, if I use that platform, what am I seeing? When I log in?
When you log on, you will think you're on any other kind of cloud environment that you're normally used to doing, except it's based on the architecture that's behind it.
So I just log in via a web browser and then there would be.
If that's your choice, yes. You can do command line interface, you can graphical user interface, you can do a cloud interface, you can do a web browser interface. Everything that we know today is all usable with CCAC.
And you said the interface, I guess, what are we necessarily seeing? I mean, is it a choice of services that we're exposing?
Well,
or-
this is an infrastructure.
Okay,
What you want to install on it, what applications you want to do on it, it all depends on the users. We're working with, what's this, CyberRing, the CyberRings people.
Virginia CyberRing?
They want to have certain kinds of things on there for their student body. We've talked about them. Everything we showed them, say, yeah, that's the underlying infrastructure. I said, I said, what do you do today on AWS? I said, well, we put our application, okay, you put them over here. It's no.
so would it be like somewhat similar to like the AWS console?
Yeah, similar to that concept, yeah.
If I'm VPCs,
Yeah.
NCPs, stuff.
Yeah.
Got it.
API, REST APIs,
Okay.
that stuff like that.
Got it.
Okay,
It's just what it doesn't, right now you have to decide if you're going to your AWS or you're going there. So I'm just saying, as a user right now, you can decide what goes, like you semi-own your own environment, and the future will be like you go and the system has an access to your own environment and can do it, right? So it's it's the short term versus long term of how this should look like is very different, but you have now access to Z and powers, which is from AI perspective, right, very, very important.
Well, thank you
How
very
many
much.
how many different access points do you see for Z16? I mean, there's talk here about putting it more connected with the rest of the Virginia power environments and having a unified interface. Is the other side of that in terms of skills building as well? So there's like the research aspect of it, of what we can do with existing data, and then there's the skills building aspect of it. I'm just wondering how you see that unfolding in terms of.
Right,
makes
right
sense.
now, we have major Virginia universities, say 7, 8 of them. As part of the work group, initial work group, and we have another 7, 8, 10 selected industries. This is just the start. The idea is to serve the whole Virginia. Whole Virginia has 42 educational universities, educational entities. So we will start with, I don't know, 3, 4, 5, go to 40, 50, 100.
Because Ben didn't commented also, you know, the important part for us is also to educate students, right? Going back the same as Mary commented on quantum. There are, you know, opportunities to participate. The community of System Z has well-defined internships for students, right? So if you are interested, right, the education part on just Z is additional thing that can be added to it, not just the part of the actual usage of it, right, but the education as well. Thank you, Ben. Thanks. Thank you. Yes. Thank you.
I'll probably visit Chennai.
Well, thank you, everybody.